All right, so this is another question that's not in your binder, but you should have printed or looked at the PDF file ahead of time here. So for 0 to 6 seconds, a screensaver on a computer screen shows two circles that start as dots and expand outward. So hopefully you can picture that. Now hopefully, and it's been a while, especially because we haven't been in school, that you can picture as the circle expands, it's getting bigger and bigger and bigger and bigger, which should lead you toward related rates thinking. At the instant the first circle has a radius of 9, so that's my first piece of information. The radius is increasing, so the radius is increasing, that's the rate of the radius. dr dt is increasing at a rate of 3/2 centimeters per second. Find the rate, so here's your calculus, of the area, so find d a dt. The circle is changing at that instant, indicate units of measure. So I think this is, although it might seem a little overwhelming, I think this turns out to be a really, really, really nice problem. So literally they're just asking you to find dA dt. They're not giving you the formula. You should know the area of a circle is pi r squared. All right, and dA dt means they want you to take its derivative. So all I'm going to do is wrap that bear up and say I'm going to derive this with respect to time. So everybody gets a derivative with respect to time, so this becomes dA dt equals, bring that 2 down, 2 pi r times dr dt. And watch how nice this is. You're asked to find dA dt, so we currently do not know that. I have my 2, I have my pi, they gave me a radius of 9 and a dr dt of 3/2. These 2's can cancel. 9 times 3 is 27. So I would say dA dt is equal to 27 pi. Now, just again, unit-wise, think common sense. Area has to be in units squared, and it's the rate with respect to time. So I'm going to say this is centimeters squared per second. Area tells me that it's squared. The rate tells me that it's per second. Part B, again, I think, although it might seem wordy, it's very friendly, so this might be one we need to slow down and do again. The radius of the first circle is modeled by this. Okay, so again, I just want to be clear, this is the radius, where W of t is measured in centimeters. At what time is the radius of the circle increasing at a rate of 3 centimeters per second? Okay, so let's just think about what they gave us. They gave us the radius. That's my W of t function. The question is at what time? So let's just be clear what we're solving for. The question is asking you to solve for t. At what time is the radius of the circle increasing? So the radius increasing means dr dt. And another giveaway is look at those units. Centimeters per second would definitely tell me that's a rate with respect to time. So I'm not going to use pi r squared this time because they told me what they want me to use for radius. They want me to use that given function. So W of t, here's the radius. And all they want me to do is take the derivative with respect to time. So box it in, say I'm going to derive with respect to time. So this becomes the derivative of W is dW dt. 12 is a constant, so its derivative is 0. This is just the derivative of an e function. Leave it alone. Then times the derivative of the exponent. The derivative of 0.5t, of course, is just negative 0.5. Okay, so you leave it alone for e's, and then you derive the exponent. It's with respect to time, so I don't need to do anything with that t there. And then again, I'm just going to plug in everybody I know. I feel like my variable here might be misleading. W of t stood for the radius. And so I used r here, but I didn't use r here. So this dr dt is equivalent to my dw dt because w represents the radius. So I can plug in 3 here. Negative 12 e to the negative 0.5t times negative 0.5. Remember, e is a number you should know. So I'm just going to clean this up. Negative 12 times negative 0.5. So negative times a negative makes a positive. 0.5 is really half. Half of 12 is 6. So I have 3 equals 6e to the negative 0.5t. To get that t by itself, I think is fairly nice. I'm just going to divide both sides by 6. So I've got a 1/2 here. I'm just going to carry on over here. I have 1/2 equals e to the negative 0.5t. To solve an e equation, I'm just going to take the ln of both sides. So I've got the ln of 1/2 equals negative 0.5t ln of e. ln of e is 1, so that disappears. So I'm going to divide by negative 0.5. Or you could multiply both sides by negative 2. So let me just carry over here. I'm just going to say it's the ln of 1/2 divided by negative 0.5. And we've got our answer. Part C. A model for the radius of the second circle is given by the function where f of t is measured in centimeters. And again, I think it all comes down to units. The rate of change of the radius is given here. So this is the derivative, keep in mind. Based on the model, how many centimeters does the radius of the second circle increase from 0 to 3? All right, so let's just think about it. Again, if it's very wordy, just go back to the units. It wants centimeters, right? And they gave you f prime of t. They gave you the rate of change of the radius. So they gave me centimeters per second, and they want centimeters from 0 to 3. So I think it should be obvious that we're just integrating from 0 to 3 of t squared minus 4t plus 4 dt. So I'll just talk through that. They gave me a derivative, so that was centimeters per second. They want centimeters, so I'm integrating from here to here. So once you have the setup, it turns out to be a nice problem. Just going to integrate, so that's t squared over 2. So minus 2t squared plus 4t from 0 to 3. So 3 cubed is 27 divided by 3. That's 9 minus 3 squared is 9 times 2 is 18 plus 12. Let's see, I like to do my adding first. 9 and 12 make 21 minus 18. I get a total of 3. It wanted units, so 3 centimeters. Again, if this one kind of tricked you, we haven't done related rates in a long time. This is definitely one where you probably just need to get a scrap sheet of paper and redo it again. And again, I would keep this right in your notebook so you're ready for that May 12th date.